What if the tire under every car could survive a puncture without ever going flat? Around 20% of tires are estimated to be discarded early because of punctures, pressure loss, and related damage, representing roughly 200 million tires and about 2 million tons of material every year. Chinese manufacturers are already producing airless tires for smaller vehicles, while engineers work toward making the technology practical for ordinary passenger cars. A normal tire depends on compressed air to support the vehicle. In a 2,000-kilogram car, 4 tires carry roughly 500 kilograms each before passengers and luggage. Airless tires replace the supporting air with flexible spokes, arches, or honeycomb structures. When the tire hits a bump, these sections bend and recover their shape. The tread still uses rubber, but the supporting air chamber is gone. A normal tire loses pressure when a nail or sharp object creates a path for air to escape. An airless tire has no pressurized chamber, so that failure cannot happen in the same way. The tread can still be damaged, but the tire does not suddenly collapse. For a fleet with 1,000 vehicles, reducing tire failures can also reduce roadside repairs, replacement costs, and downtime. That makes airless tires especially interesting for commercial operators. Many airless designs use repeating structures between the wheel and tread. These sections act like small springs, bending when they contact the road and returning as the wheel rotates. A honeycomb pattern provides strength without filling the entire tire with heavy material. Engineers can change the thickness and shape of these sections to control stiffness. The internal structure is therefore the key part of the airless tire. China did not invent airless tires. Michelin and Hankook have also developed non-pneumatic designs. Chinese manufacturers are already producing airless products for scooters, bicycles, carts, robots, and industrial vehicles. That gives factories valuable real-world experience. Producing 1 million tires also allows manufacturers to identify production problems much faster than small laboratory trials. China's large rubber, plastics, and electric mobility industries make scaling this technology easier. A fleet of 10,000 vehicles traveling 20,000 kilometers per year covers about 200 million kilometers combined. Even a small failure rate can create thousands of maintenance events. Each event can mean a replacement tire, labor, and lost operating time. Airless tires could remove pressure-related failures from that calculation. For a private driver, a flat may happen once every few years. For a large delivery fleet, repeated failures can become a serious operating expense. Run-flat tires use reinforced sidewalls that allow a vehicle to continue driving after losing pressure. Many are designed to travel around 80 kilometers after a puncture under specified conditions. The problem is that stronger sidewalls can increase stiffness, weight, and cost. A run-flat driven without pressure may also need replacement. Airless tires take a different approach by removing the air dependency completely. Tires constantly flex while moving, and that creates heat. At 100 kilometers per hour, a car travels about 27.8 meters every second, producing thousands of tire deformation cycles during a long journey. Airless materials must handle this repeated movement without overheating or weakening. A design that works well on a scooter at 40 kilometers per hour may behave differently on a car at 120 kilometers per hour. High-speed heat management is therefore one of the biggest challenges. Air weighs very little, while a structural replacement requires physical material. Suppose an airless design adds 5 kilograms at each wheel. 4 wheels would add 20 kilograms to a 2,000-kilogram vehicle. That is only about 1% of the vehicle's mass, but weight matters greatly in electric vehicles because extra mass can reduce efficiency and range. The tire therefore needs to be strong without becoming too heavy. Tires also act as part of the suspension system. Their sidewalls and air pressure absorb some road impacts before those forces reach the cabin. Airless tires have to recreate that behavior using their internal structures. Too much stiffness can create a harsh ride, while too much flexibility can affect handling. A tire working at 30 kilometers per hour also faces very different forces from one operating at 120 kilometers per hour. Comfort and stability are just as important as puncture resistance. Open spaces help airless tires remain flexible and lightweight, but those spaces can collect mud, snow, and gravel. Unevenly trapped debris can make the wheel unbalanced and create vibration. At 100 kilometers per hour, even small imbalances can become noticeable. Engineers therefore have to protect the internal structure without blocking the spaces that make it work. It is one of the less obvious problems with the design. Michelin estimates that 200 million tires, or about 2 million tons of material, could avoid premature waste each year by eliminating punctures and pressure damage. Some airless designs may also use replaceable treads, reducing waste even further. Scooters, robots, and industrial vehicles are becoming early testing grounds because they operate at lower speeds and simpler conditions. This gives manufacturers thousands of hours of real-world data before moving toward passenger cars. With modern tires expected to survive around 100,000 kilometers, airless designs still need to prove long-term safety against heat, rain, potholes, and repeated braking. China's advantage may be manufacturing rather than invention. The country already has large supply chains for rubber, plastics, tires, electric vehicles, and industrial equipment. Increasing production from 10,000 units to 1 million units allows factories to find defects faster and spread production costs across more products. Better molds and automation can also reduce manufacturing costs. If airless tires become cheaper through scale, passenger cars become a much more realistic target. Suppose a normal tire costs $100 while an airless version costs $200. 4 tires would mean an extra $400 before installation. Many private drivers would not pay that simply to avoid punctures. Fleet operators may think differently because reduced downtime can save much more than the additional tire cost. That is why commercial fleets could adopt airless technology before ordinary consumers. Eventually, mass production has to bring the price close to conventional tires. Could traditional tires disappear? Not anytime soon. Pneumatic tires already offer an excellent balance of price, weight, comfort, and performance. Airless tires must match those advantages while adding puncture resistance. The transition would likely begin with industrial vehicles and fleets, then move toward passenger cars as the technology improves. If production reaches millions of units, manufacturing costs and reliability could improve significantly. The technology does not need to beat normal tires everywhere, only in enough important areas to make switching worthwhile. A spare wheel, tire, and jack can add several kilograms to a vehicle while remaining unused for most of its life. If airless tires become reliable enough, that equipment could eventually disappear from many cars. Drivers would gain extra storage space and avoid one of the most frustrating roadside repairs. No pressure checks, no jack, and no spare tire waiting in the trunk. The change would be small physically, but significant for how vehicles are designed. Airless tires are real, but an indestructible tire does not exist. The major challenges are heat, weight, comfort, debris, durability, and price. Chinese manufacturers are already gaining experience with airless designs in smaller vehicles, while global tire companies continue developing passenger car versions. If those problems are solved together, the technology could slowly move from specialist vehicles into everyday cars. The flat tire may not disappear tomorrow, but the technology needed to make it far less common is already being built. If you enjoyed this video, don't forget to like, share, and subscribe to our channel.